This problem again uses the Gauss law, and we have to calculate the electric field within a cylinder. So let's get into this problem. So you have a cylinder. So let's say you have a very long cylinder, and I'm using a dotted line here just to represent it is infinitely long. It's a very long cylinder. So this is a very infinitely long cylinder. Let me draw a little better. Okay. So you have a long, infinitely long cylinder. The radius of the cylinder is 2 centimeter. So this is the center line. This is the center line. So this distance is 2 centimeter. The radius R is 2 centimeter. And now we have to find out the electric field at a distance of 1 centimeter from this point. Let's say 1 centimeter. At this point you have to find out the electric field. How do we do that? So this is an infinitely uniform, and this one is charged, and it is uniformly charged. The charge density is given, and you have to find out what is the electric field at this point within the cylinder. So we have to assume, or we have to create an imaginary Gaussian surface. In this case, as this is a cylinder, I'm going to draw a cylinder as well, passing through this point. So this is a Gaussian surface, and at this point we have to find out the electric field. The charge density is given. Let me write down here, charge density. I'm simply denoting the charge density by rho here, which is given by 18 microcoulomb per cubic meter. Let me change this one to the microcoulomb to coulomb. So this one is 18 times 10 to the negative 6 coulomb per cubic meter. That's the charge density. It's a given quantity, and this is an imaginary, the Gaussian surface passing through this point P. And the distance, this distance is given, I'm calling this as R, which is 1 centimeter. 1 centimeter. Okay. So now let me use the Gauss law here. What does the Gauss law tell you? It simply tells you this is the total flux, or this is the electric field, and this is the elementary area. Q enclosed divided by the epsilon naught. Okay. Let me call this length L of the cylinder. Now you see. So the charge density is positive. That means the electric field direction is radially outward. So at any point, if you take the electric field at any point, it is always outwards. it is always outwards, and it is always perpendicular or parallel to the surface here. So the area vector and the electric field vector are always parallel, and there is no electric field coming out of this surface or this surface. So these two are parallel at all points, and there is no electric field coming out of this surface, and there is no electric field coming out of this surface. So we can simply write down this integral as the electric field times the total area, the surface area. What is the surface area? The surface area is 2 pi r L. Why did I choose this way? Because you see there is no electric field coming out of this surface, so we do not need the integration, and there is no electric field coming out of this surface. So the surface area of this cylinder is simply equal to 2 pi RL and E, and these two are parallel at all points. Okay. And now, what is the charge enclosed within this region, or charge enclosed by the imaginary Gaussian surface? So this is simply equal to rho times the V. This is the volume of the enclosed surface divided by epsilon naught. Okay. Let me write down here, or maybe I'm just writing this part here. Rho is given, and the volume of the cylinder. What is the volume of a cylinder? The volume of the cylinder is pi r squared times L divided. This is the epsilon naught. Alright, so now see, this L and this L cancels out. 1r and the 1r cancels out. Pi and the pi cancels out. So the electric field now is given by, the electric field can be written now as rho r divided by 2 epsilon naught. Plug in all the values. Rho is given 18 times 10 to the negative 6. The r is given 1 centimeter, and we have to change centimeter to meter, which is 1 times 10 to the negative 2. 2 epsilon naught is 8.85 times 10 to the negative 12. Use your calculator, and the number you will get is 10.2 times 10 to the negative 3 Newton per coulomb. That's the value, you'll get it. Alright.